Another interesting application of exponential growth and decay is carbon dating. When scientists want to know how old something is that used to be alive and isn't any longer, they look at how much of the radioactive element carbon-14 remains in it compared to how much they believe was supposed to have been contained in it at the time it was alive. Carbon-14 is called an isotope of the carbon atom, and it decays, it says here, has a half-life of 5,750 years. So every year, there's a little bit less of it, but it decays so slowly that we can use it to look back a long time, see how long it's been since something died. So the radioactive element carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that a linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Okay, so the only information we need here is that there was 22.3% of it remaining. We know because of the time it actually takes for carbon-14 to decay, scientists know that the rate it decays at is 0.00012 negative. And we know how much it starts with. We know it starts with 100%. So for this particular case, we've got 100 e to the negative 0.00012 t. For all carbon dating, we would start with that part of the equation, and all we need to know is how much was left. Well, if we had lost 22.3%, that leaves 77.7%. I think that's right. I'll do 100 minus 22.3, 77.7%. Okay, so carbon dating, always 100 times e to the negative 0.00012 t, and that's going to be equal to how much of the carbon remained. And if we can solve this equation, we can find how long this thing has been dead. And we talked about solving this equation a couple sections ago, or maybe in the last section, I don't remember. When our variable is stuck up here in the exponent, we're going to have to involve logarithms. That's why we talked about them, so we could deal with situations like this. First step, though, is to isolate the exponential part on this side. We don't want that 100 out in front. So I'm going to divide both sides by 100. I apologize, my handwriting is much better on the actual board. So we get 0.777 equals e to the negative 0.00012 t. Now we can use the log of both sides, and we're going to use natural log since we're dealing with e. So we'll get the natural log of 0.777 on the left, and the right will really simplify because the natural log of e to a power is just the power. Remember what the natural log is. It's asking the question, e to what power would be equal to e to that power? The answer is going to be that. So negative 0.00012 t. And all we have left to do is divide by negative 0.00012. And that's how many years the Dead Sea Scrolls, or rather the wrapping for the Dead Sea Scrolls, that's how long that papyrus has been dead. That isn't a very satisfying answer. So go to natural log of 0.777, divide that by negative 0.00012, and that gives us 2,102 years. Now, I would say maybe around 2,000 years. I wouldn't try to be specific to the individual year, but that's the number we get. Okay, so there's the process. I said it's going to be the same every time, which means the solving part's going to be the same every time also. So all we really need to do here is do the natural log of whatever percent of the carbon is remaining divided by that rate. Let's look at another quick example here just to illustrate how simple that is. In 1970, Amos Flora of Flora, Indiana, discovered teeth and jaw bones while dredging a creek. Scientists discovered the bones were from a mastodon and had lost 77.2 of their carbon-14. So how old were they at the time they were discovered? They had lost 77.2. Right, so go back here. I guess I'll redo it because I smudged it pretty badly. If it lost 77.2, then 22.8 remain. So we've got 22.8. On the other side, we've got our 100 times e to the negative 0.00012 t. Oh, my bad. There. Divide both sides by 100. That's going to give us 0.228 is e to the negative 0.00012 t. A lot of repeatedly writing the same stuff here, which is why I kind of like the shortcut. We know what we're going to do from here. We're going to take the natural log of both sides, which is going to give us the natural log of 0.228 on the left. And when we do the natural log of this on the right, it's just going to give us the exponent, negative 0.00012 t. Divide both sides by negative 0.00012. And we get whatever that is. Natural log of 0.228 divided by negative 0.00012. And we see that the mastodon there had been dead 12,320 years. Okay. The shortcut, natural log of how much was left, divided by that number, or the rate that it had been decaying at, and that'll give you your answer. See you next time.